Everyone. So let's talk about the next topic now, which is temperature and heat. And we will use our common sense to describe them. Let's define our system here. So once I define the system, I have a boundary of the system and I know the environment. And let's say the temperature of the environment is equal to the temperature of the system. Two system, because the environment also is a system, two thermodynamic systems, they have the same temperature. What it means? They are at equilibrium. When they are at equilibrium, there is no exchange of any energy. They are all their property are settled down. Okay, so there is no exchange of energy here. So we say that there is no exchange of heat. And this is our common sense, what's that? Two systems, they have same temperature, but there is no heat flow between them. That's common sense. So the heat flow is zero. Okay. Let's take the situation when the system is hot than the environment. So remember the hot coffee in the environment. Where the heat will go? Of course, heat will flow from the hot system, the hotter system. Okay? So the heat flow from hot coffee to the cold environment. So in this case, we say that the heat is negative because it's going out from the system. The system is losing heat. So it's losing energy as heat. When the temperature of the environment is hot, heating up something in the oven, so this system will gain energy from the oven. Okay? So it will absorb heat. We say the system will absorb heat and the heat is positive. So the heat, we call it Q. That's the energy transferred between a system and its environment because of the temperature difference between them. So as you can see, when the temperature is different, the difference in temperature, that's what tells you if the system is absorbing heat or losing energy as heat. What is the unit of heat? So we just said heat is just energy. So the classical unit, that joule. But it turns out that it has another energy, which is calorie. So what is 1 calorie? 1 calorie is the amount of heat to raise the temperature of 1 gram of water, liquid, by 1 degree Celsius. Just 1 gram of water, and you heat it up with 1 degree Celsius. The energy required in this process is 1 calorie. Why the heat has different units? Well, because it turns out historically we didn't know that heat is energy. What people before believed in is that there is a fluid called caloric fluid. This caloric fluid exists in hot environment, hot system. And when the system is in contact with other system, this caloric fluid will flow to cold region, will flow to the cold region. So this is from where come calorie. If you need to read about it, it's called caloric fluid. Intel Joule come with an experiment to prove that heat is energy. Well, what he did, that's a very interesting experiment I'm sharing with you here. And this will bring us to physics 1, to mechanics. Let's say you see here, you recognize a lot of things. We have a body here with mass m at a certain height, z. And there is a pulley here, there is a rod. The rod is attached to a rotating paddle. When this body is released, when it goes down, it rotates this, so the paddle starts rotating inside the fluid. Conservation of mechanical energy, tell me. this system, it's released from rest. So how we can write the conservation of energy? Basically, we have mgz, that's the potential energy, okay, is equal to what? To the kinetic energy here, half m v final square, assuming that v initial is 0. Do you agree? Common sense. So we know how to calculate z. We can find a way how to calculate the speed. And we can compare these two expressions. That's what Joule did. What he found, they are not equal to each other. So there is something wrong here. They are not equal to each other. Why is that? So he found out that these two energies are not equal to each other. What it means, energy is not conserved, that's not possible. So he noticed that the fluid became warmer. The fluid heats up. Okay? So this energy is used, some of this energy is used to heat up the fluid. And here where he did use that, what we call heat Q, that's just another form of energy. So basically the right conservation energy should be like that, plus heat. Okay, so the potential energy is converted not only to kinetic energy, but also into heat. So we know, we will see later how to calculate the heat. So that's what he did, and he calculates a certain number of calorie, heat in calorie, and he calculated this energy, the remaining energy in joule. These two energies should be equal to each other. When he did that, he did use that 1 calorie is 4.18, basically, joule. Okay, so that's the relationship, how to go from calorie to joule and from joule to calorie. So now, how to calculate heat? We will use the same idea that we used for thermal expansion. The system, it has temperature T, and we raise temperature from T to T plus delta T. So there is an increment of temperature, delta T. What is the heat? The heat, the energy used to heat up a system, well, depends on the amount of the system. If you tell you what is the energy required to heat your water, you tell me, okay, what is the amount of water? Are we heating 200 milliliter, 500 milliliter, or 1 liter? The heat will depend on that. So it depends on the amount of matter that you want to heat up. So it depends on the mass, let's say. It depends, of course, on the temperature, to which temperature you want to go to heat it up. And there is another factor that tell me what you are heating up. So that's what we call specific heat. There is another formula for the same thing that we can see also, C times delta T. And what is C? That's heat capacity. So you can see that heat capacity, what is it? That's just specific heat times the mass. Why we call it heat capacity? You see here, this formula, does it remind you something? Well, that's basically electrical capacity, it isn't? Electrical capacity, what is it? Q equals C delta V. Okay, what is C? That's capacity. That's capacitance. Q is the charge, delta V is the difference in potential. So we have a list of some of this heat capacity, specific heat, so this is specific heat. There are 2 units, be careful. There is calorie per gram per Kelvin, and there is joule per kilogram per Kelvin. Well, this depends on your problem. So basically, if you are talking about gram, it's better to use calorie. But if you are talking about kilogram, it's better to use joule. So it depends on this situation. So what I will do, generally I use this often, but in some cases I might use calorie. And there is here a last column that's molar specific heat. So we will not talk about it a lot in this chapter. So the molar specific heat, basically, that's when we express the heat as this: C times N times delta T. N is the number of mole. So if I use, instead of mass, I use number of mole, I will talk about molar specific heat. Okay? We use it more for gas, basically. There is an important thing to add here. This formula that I just described, it can be used when we have the same state. What I mean by same state? Let's say I talk about water, liquid water, and when I change temperature by delta T, the water remained liquid. Or I take water in solid form, so this ice, and when I change it by delta T, the ice remained ice, it will not melt. When there is a melting of ice or evaporation of water, there will be another form of heat, called heat of transformation. Heat of transformation. Let's say we start from ice at a certain temperature. So when you give the energy heat to the system ice, when the ice it will warm up, you go from certain temperature, let's say minus 18 degree, and you raise the temperature, okay? You warm the ice until you reach 0 degrees Celsius. So we are talking about atmospheric pressure. At 0 degrees Celsius, you have a coexistence of solid state and liquid state. So the ice start to melt. But what will happen? Very interesting observation. The ice and water, both of them, are at the same temperature, 0 degrees Celsius. So you are giving the system heat, but the temperature will not raise up. It will stay stable at 0 degree until all ice became liquid water. At this point, the temperature starts to raise up. So the temperature raise up when you have one state, not the coexistence of two states. Okay? That's very important. Talking here about equilibrium. So here we have freezing. Freezing, what is the opposite of freezing? Melting. I can go from liquid state and I freeze the water, or I can go from ice and melt it. So when you have transformation, state transformation or phase transformation, we have a heat. This heat, this amount of heat, okay, is used just to change, to transform the state. Okay, so this heat is called generally L times the mass. Okay, so L is called the latent heat or heat of transformation. Okay, so it's tabulated. Found a table for heat of different transformation: freezing, melting, or evaporation, vaporization, condensation. Okay, so any phase transformation, it has heat of transformation associated to it. So this is L of fusion. This is L of vaporization. Here, L of vaporization times the mass. What is the mass? That's the mass of, let's say I'm going from ice and I melt ice. What is M? That's the mass of ice that melt. Mass of ice that melt. So in general, what we can say, the M is the mass of the object that transforms. Okay. So with this, we know everything about heat for solid and liquid, and we can start our problems.